Okay, today we will start chapter 7, and hopefully by the end of the class, so I guess there's 3 more lectures including today, we'll get through 7b, or at least as much of 7b as we can. Okay, so let me just remind you of what we've done in this course. Okay, so at the start of the course, what we did is we studied vector spaces, subspaces, axioms, all kinds of stuff. That was in chapters 1 to 2. After that, we studied maps between vector spaces. And that we sort of broke that up into 2 parts. Just in general, maps between any 2 vector spaces, and then we studied operators from a vector space to itself. Right? So that was in chapters 3 and 5. In chapter 6, we studied inner product spaces, which are special kinds of vector spaces, equipped with a little bit more structure than inner product. Then question marks, and then profit. That's the rest of your life. So what should go in these question marks? Somehow we need to study maps between inner product spaces. But in fact, the most important maps between inner product spaces are the operators on inner product spaces. So what goes here is study operators on inner product spaces, right? Because once you have this additional structure of an inner product space, then you can say more things about maps between those inner product spaces. Oh, okay, and I guess also somewhere in here, also, we did a quick digression on polynomials, but that's not really linear algebra. But I'm a mathematician, which means I like to be complete in the things that I say. Okay, so in this chapter, therefore for the rest of the course, throughout, let me maybe put this in a different color. So V and W are going to be finite dimensional inner product spaces over F. Okay, so I'm not going to keep saying that hypothesis, but both finite dimensional and equipped with an inner product. Okay. So let's begin. I mean, I guess technically we are going to start by just studying a thing that's not necessarily an operator. So maybe even here I could study operators and linear maps between inner product spaces as well. But most of our focus will actually be on the operators. Okay, here's the definition. Okay, so suppose that T is a linear map from V to W. And again, I'm not saying this because I've made the hypothesis consistent throughout. V and W are finite dimensional inner product spaces. Okay. Then the adjoint of T is the function denoted T star from W to V. Okay, so it goes in the opposite direction as T. And how is the adjoint defined? It's defined via the following property. If you take the inner product of TV and W, so this is the inner product in W, right? This is going to be equal to the inner product of V and T star of W. This is going to be true for every V and V and W and W. Okay. So just as I said, this is the inner product in W, right? Because those vectors are both in W. This is the inner product in V. So it seems like I haven't really defined what the function T star does. In fact, it's not even clear that such a function exists. Right? How do you know that there is going to be a vector T star W that satisfies this property? And so why does T star exist? Okay, well, let's see that it does. So suppose that T is a linear map from V to W. And let's fix a vector W and W. Okay, then we can consider the linear functional V to F that maps V to the inner product of TV and W. Okay, the reason that this is a linear functional is because it's the composition of two linear functionals, right? So maybe I'll put that in blue. So this map, this is a linear functional. Since first you go from V to W, that's via T, that's a linear map. And then you go to F, where this thing is the linear map where you just take the inner product with W. We proved that that thing was a linear map. Right, so this is the composition of two linear maps, therefore it's linear. So this is a linear map that depends on T and this fixed choice of W. Okay, but the point is that by the Riesz representation theorem, this linear functional must be given by inner product with some vector. So by the Riesz representation theorem, this map, I mean, I should say there exists a U in V such that this map is just the inner product with U. Every linear functional is given by inner product with some vector. So this map, which depends on T and W, spits out a unique, I should say a unique U and V. And this U, this is the thing that we call T star of W. Therefore, if you fix the map T, for every single W you do this process that gives you a unique vector T star W. Therefore, this does define a function T star from W to V. Right, this is in V. So it's not that obvious that just by the definition, if you look at the definition, it's not that obvious that T star should exist. But if you use the Riesz representation theorem, you'll see that this actually does define a function. Okay, so as with any first example, any time you see a definition, the first thing you should want is an example. Okay, so let's let T just be any old linear map between two inner product spaces. Right, so anytime you see Rn or Fn, we're going to assume we're using the standard Euclidean inner product. So suppose that this map is defined by T of x1, x2, x3, x4 equals, I don't know, x1 minus x3 comma x2. Let's compute the adjoint. T star from R2 to R4. Okay, well, let's fix a point y1, y2 in R2. I'm trying to figure out what does T star do to this point in R2. But the definition of the adjoint says that if you look at V comma T star of W, that's this, that should equal T of V, right? What is T of V? T of V is this vector, x1 minus x3 comma x2, the inner product with W. Right, that's what it would mean for T star to be the adjoint. Okay, but this inner product, again, is just the standard dot product on R2. So this thing becomes x1, y1 minus x3, y1 plus x2, y2, right? All I've done is I've just done the dot product. Now the question is, we're trying to figure out is what is T star of y1, y2? Well, it's just the thing that when you take the dot product with x1, x2, x3, x4, gives you the required result. So that must mean that this is actually going to be y1, y2, minus y1, 0. Right? That's what it's got to be. Therefore, I know exactly how to compute the adjoint of this map. I've told you exactly what the adjoint does. So T star of y1, y2 just equals y1, y2, minus y1, 0. Okay, now notice something. That this adjoint map is, again, a linear map. If you prefer, you could represent this with a matrix, I guess. You just need to know what those the two standard basis vectors. So it's the map given by multiplication by this matrix. So this is a linear map. Notice that by definition, the adjoint is just a function. And it's not that clear that it should be linear, but it is in fact always linear. So it's a result that the adjoint of a linear map is a linear map. So let's prove that. If T is a linear map from V to W, then T star is a linear map from W to V. Okay, let's prove this. Okay, so it's, again, anytime you try to prove something about something new, it seems kind of mysterious, right? Because you don't know what the, at this point, you don't know what the adjoint is. You've seen the definition once. Seeing the definition once is not the same thing as knowing what something is. But we can break it down so that we have something to aim for, right? So I need to show that T star is a linear map. That means I need to show that T star respects addition and T star respects scalar multiplication. That's my job. In fact, what I'll do is I'll show that T star respects addition, and I'll let you do the proof that T star respects scalar multiplication. It's also in your book. You can just read there. Okay. So fix W1 and W2 in W. Right. So we want to show that T star of W1 plus W2 is the same thing as T star W1 plus T star W2. That's our goal. Okay, now, for every V and V, I'm going to just try to use the definition of the adjoint. So V, if you take the inner product of V with T star of a vector, it's the same thing as taking the inner product of TV with just the vector. This is by the definition of the adjoint. And this is the same thing. Well, I can use the fact that inner products are additive in the second slot, like this. And again, I'm interested in these adjoints, so I can use the property of the adjoint to write these as V1, just V, there's no V1, V comma T star of W1 plus V comma T star of W2. And then I again use additivity in the second slot to write this as V comma T star W1 plus T star W2. Okay, but this is true for every single V in V, right? This held for every V in V. In other words, what this means is that the functions, that this function equals this function, or linear functional, right, as linear functionals. Because they both do the exact same thing to every V. But part of the Riesz representation theorem was that something about uniqueness, right? In other words, if you take the inner product with u1 and you take the inner product with u2 and they give you the same functional, then u1 and u2 must be the same vector. Go back and look at the uniqueness part of the Riesz representation theorem. By the uniqueness part of the Riesz representation theorem, this means that this vector must be equal to this vector. And then I'll leave you to handle the scalar multiplication thing, but you do the same, you basically do the same thing. Okay, so good. So now we know that if T is a linear map from V to W, then the adjoint is also a linear map. And now that we have this brand new linear map to play with, the adjoint, we should try to understand the basic properties of the adjoint. We should try to understand the null space of the adjoint, the range of the adjoint. We should try to understand the matrix of the adjoint. That's basically what we'll do in the rest of this section, things that I just said. Okay, and a bit more. But once you have a linear map, you should basically ask these very fundamental questions first. So basic properties of the adjoint. I feel like I'm getting some lag on my screen. So here are 5 basic properties of the adjoint. One is if you take the sum of 2 linear maps and take their adjoint, that's the same thing as taking the sum of the adjoints. Okay. 2, if you take a scalar multiple of T and take the adjoint, here the result maybe is going to be something you need to remember. You can pull scalars out of an adjoint except at the expense of a complex conjugation. So this is for all lambda and f and T linear map from V to W. Okay, 3, if you take the adjoint of the adjoint, this is just the map T again. 4, if you take the adjoint of the identity map, it's just the identity map. So here, of course, I is the identity map in operators from V to, in the space of operators. And then 5, if you take the composition and you take the adjoint, it's the same thing as composing the adjoints in the opposite order. This is for all T in, say, LVW and S in LWU. So some very basic properties of the adjoint, I think probably all of which are easy enough to remember, except you need to really remember that when you pull a scalar out of an adjoint, you need to make sure to take the complex conjugate of the scalar. Okay, let's prove these things. I mean, we want these things to be true, I think. Let's prove them. And of course, for number 2, if the field you happen to be working over is R instead of C, then you can just pull out scalars if you're working over the real numbers. But when you pull out that scalar, you should be thinking, oh, I'm pulling out the complex conjugate of the scalar, because that's really what you're doing. You just don't see it if you work over R. Okay, so 1, suppose that S and T are linear maps from V to W. I'm trying to prove something about the adjoint. I need to use the adjoint property. Okay, so now if V is in V and W is in W, then the property of the adjoint says that if you take the inner product of V and the adjoint map applied to W, it's the same thing as taking the inner product of the original map applied to V and W. This is the adjoint property. Okay, but then we know what the sum of S and T does to V. It just spits out SV. Okay, I guess I'm doing 2 steps here, but I think you can handle those 2 steps. Then you use the property of the adjoint again. So the adjoint has the property that basically you get to switch where the function goes at the expense of the adjoint. And then you now use the linearity of not the linearity, the additivity of the inner product in the second slot. Okay, but again, this is one of these cases where this vector and this vector have to be the same by the uniqueness part of the Riesz representation theorem. Right? This equality is true for every vector v and v, which means that taking the inner product with this vector and taking the inner product with this vector yield the same linear functional on v, which means that those are actually the same vector. Okay, so all the things that I just said imply that this equals this. And this is true for all w and w, right? Because the w I picked was arbitrary. This means that this function equals this function, which is what we wanted to show. So again, just a little exercise in using this new definition to prove something new. Okay, so since 2 is actually a little bit different because you need to take the complex conjugate, let's just do it together. So suppose that T is a linear map from V to W, and lambda is a scalar. Again, I want to use the property of the adjoint. What's the property of the adjoint? So let V and V and W says that if you take the inner product of V with the adjoint of lambda T applied to W, it's the same thing as taking lambda T of V inner product with W. Okay, now this lambda, since it's in the first slot of the inner product, you can just pull it out as a scalar. Now you use the property of the adjoint to swap where the T is. So this is V T star W. And now the thing is, I want to push the lambda in to the second coordinate of the inner product, but you can't just push a scalar into the second coordinate. You need to take this complex conjugate. So this is V comma lambda bar T star W. And again, same reasoning. Taking the inner product with this vector is the same thing as taking the inner product with this vector. So those two vectors are the same. That's true for every W and W, which means that the adjoint of lambda T is the same thing as the adjoint of T times the scalar lambda bar. Okay, now part 3, I need to show that taking the adjoint twice returns the original function. So suppose that T is a function from V to W. As always, if V is in V and W is in W, I want to understand the adjoint of the adjoint. So I want to use this adjoint property applied to the map T star. So what does this say? Oh, it's actually even, right. So here we want to use the property of being the adjoint of T star, which is a map from W to V. So what does it mean? What does the adjoint property mean? It means if you take now a vector W and you apply the adjoint of the map to a vector V and take the inner product, it's the same thing as taking the map applied to W and V, that inner product. So I'm applying the adjoint property except to the map T star, which is a map from W to V. Okay, I'm trying to figure out, I want this to be the same thing as the inner product of W and TV. So somehow I need to get rid of this adjoint. How do I get rid of the adjoint? To get rid of an adjoint, you should use the property of being an adjoint, because that's what gets rid of one one of the stars. In order to do that, though, I need the T star to be in the second slot of my inner product. But the inner product is conjugate symmetric. So you can swap at the expense of the complex conjugate. Okay, now this T star is in the second slot of my inner product, which means I can use the property of it being the adjoint to T to say that this is the same thing as this, of course, with the complex conjugate taken. But now the inner product has conjugate symmetry, which means I can flip the inner product by taking a complex conjugate. But if you conjugate twice, it's like not doing anything at all. And again, this and this must be the same vector. And since that's true for all v and v, it means that T star star has to be the same map as T. Okay, so that may be a little bit tricky. Okay, 4 was about showing that the adjoint of the identity is the identity. So let's see. So 4. Since now we're taking an operator, let's take u and v to both be in v. Okay, then what does it mean to be the adjoint of the identity? It means exactly this. If you take the inner product of v with I star u, it's the same thing as taking the inner product of I, v, and u. That's what it means to be the adjoint of the identity. But of course, the identity applied to u, that's just v comma u. And now the same trick that we've used several times, this vector and this vector must be the same vector. Since that's true for every u and u, it means that I star of u equals u for all, right? So this means that I star u equals u for all u and v, which just means that I star is the identity. That's what the identity map is. Okay, and then lastly, the 5th part was about the adjoint of a composition, right? So now suppose that T is a map from V to W and S is a linear map from W to U. Now if V is in V and U is in U, right? Because I'm interested in the composition which goes from V to U, right? So maybe I should just write that ST goes from V to U. That means I need to take a vector here and take a vector here to try to use the adjoint property. So what does it mean to be the adjoint? It means that if you take the inner product of V with the adjoint map applied to U, it's the same thing as taking the original map applied to V, comma U, that inner product. Okay, but this is the same thing as S of TV, comma U. And now I can use the adjoint of S and move just the S over to the other side. Right? This is S of something, comma U. So it's the same thing as the something, comma, the adjoint of S applied to U. Now I can use the adjoint of T. I mean, I can push the T across by taking the adjoint. So this is V, the inner product of V and T star applied to S star of U. But this is just the map T star S star applied to U. And yet again, this vector and this vector are the same vector. That's true for all U and U. This means that this map is equal to this map, which is what we wanted to show. Okay, so very basic properties of the adjoint. You can add, I mean, the adjoint of the sum is the same thing as the sum of the adjoints. If you take the adjoint of a scalar multiple, you have to, that's the same thing as first taking the adjoint and then multiplying by the complex conjugate of that scalar. Take the adjoint twice, you get back the original map. Adjoint of the identity is the identity. The adjoint of the composition is the composition of the adjoints in the opposite order. Okay, next order of business is to understand the null space and range of the adjoint. Of the adjoint map. Here's the results. So suppose that T is a linear map from V to W. Then the null space of the adjoint map. Okay, so the map goes from V to W. Its adjoint goes from W to V. So its null space should be some subspace of W. And the one it ends up being, interestingly enough, is you take the range of T, that's a subspace of W, and you take its orthogonal complement, also a subspace of W. And maybe not surprisingly, the range of the adjoint is the orthogonal complement of the null space of the original map. And then these two will follow immediately from this, but we'll write them down for completeness. The null space of the original map is the same thing as the orthogonal complement of the range of the adjoint. The range of T is the same thing as the orthogonal complement of the null space of the adjoint. Okay, and the nice thing about this result is basically only to prove 1, and then 2 will follow, and then 3 and 4 will follow from that as well. Okay, so here's the proof. Let's just prove 1 first. So I want to show that these two subspaces of W are the same. And actually, I can do it with a sequence of if and only ifs. So suppose that W is a vector in W. Then, so if W is the null space of T star, that's equivalent to saying that T star of W is equal to 0. That's just what it means to be in the null space. Okay, but then a clever way to say something that's 0, to say that something is 0, is to say that every inner product with the vector is equal to 0. So this vector 0 is exactly the same thing as if I take the inner product of this vector, I get 0 for every V in V. But hopefully by this point, if you see V comma T star W, what you want to write is TV comma W. So this is equal to 0 for every V in V. Okay, but look at what this says. This is true for every V in V, which means that this vector TV is always spitting out vectors in the range of T. And it's actually, as you take it over every vector V in V, this vector TV goes over every vector in the range of T. So what this is saying is that W is going to be orthogonal to every TV. In other words, W is orthogonal to every vector in the range of T. In other words, W is in the orthogonal complement of the range. And actually, every single one of these is an if and only if. Let's trace it backwards. So if you have something that's in the orthogonal complement of the range, it means that it's orthogonal to everything in the range. In other words, the inner product with everything in the range is 0. In other words, the inner product with TV is 0 for all V and V. So that gets you back one step. Then, of course, you go back another step just by using the property of the adjoint. And then if for every V and V, the inner product with some vector is 0, there's a unique vector like that, and it's the 0 vector. And then, of course, T star of W equals 0. That's just equivalent to W being in the null space. That's just the definition. So all this together shows that the null space of T star is equal to the orthogonal complement of the range of T. Okay, kind of a nice fact. Now, we can cleverly conclude 3 from this by just taking orthogonal complements. So for 3, you just take the orthogonal complement of what we just proved. And then we showed, I think, that if you take double perps, you just get back the original subspace, and that's 3. Or actually, it's 4. Whoops. I'll fix that in the notes. Okay, but now, if you look at 1 and 3, 1 and 3 are almost saying the same thing, right? We proved 1 for every map T. In particular, we proved it for the map T star. So for 3, apply 1 to T star. What does it say? It says the null space of T star star equals the range of T star perp. But we proved that T star star is the same thing as T. So the null space of T is equal to perp of the range of T star. And then for 2, you just take orthogonal complements again. You just take the perps of 3. Okay, so 1, I think this proof was like a little bit tricky. There were some clever ideas in that sequence of equivalences, but then once we proved that, it all crumbled before us, right? In a good way. It crumbled in a good way. It was all a lot easier than we thought it would be. Okay, and then maybe the last question I can answer today. And I really don't know if we're going to get through 7b. Maybe we'll only get through 7a in this class. Doesn't really matter. We'll finish wherever we finish, right? So we did basic properties of the adjoint. We did the null space and the range of the adjoint. The next question that you should ask is, what is the matrix of the adjoint? For some of you, this may be the first question you ask because matrices are so nice to compute with. Okay, and that sort of always happens in math classes. I'm going to give you a definition which will just tell you the answer, because otherwise I wouldn't define the thing that I'm defining right now. Right, so you can still act surprised when we get to the theorem, but if A is an m by n matrix, its conjugate transpose, the conjugate transpose of A, is the n by m matrix obtained by taking the transpose followed by the complex conjugate of every entry. Okay, so this is a well-named concept. What is the conjugate transpose? You just take the conjugate and then the transpose. Okay, so this is sometimes called the Hermitian transpose. Sometimes called the Hermitian transpose. Although your book doesn't call it the Hermitian transpose, but if you see this ever again, that's what it means. And so it's sometimes denoted with an H, but again, your book doesn't use this notation, so I won't use it. I just want you to know that it exists. Okay, so just a quick sanity check example. So of course, if you're working over the real numbers, then taking the transpose of a real number does nothing. right? So if F equals R, then the conjugate transpose, that's just the transpose. Okay, but let's just write down a complex matrix. No, 2, 3 minus I, 5I, 1 plus I, 2, 7. Okay, so I'll use this notation that I said I won't use. In general, I won't use this Hermitian transpose notation. But what do? First thing you do is you take the transpose. So it's going to be a 3 by 2 matrix. And then for each entry, I'll take the complex conjugate. So 2, 3 plus I, negative 5I, 1 minus I, 2, 7. Okay, and of course, the reason why I'm introducing this is because it's somehow going to be related to the matrix of the adjoint map. Okay, so also for that reason, sometimes people denote the conjugate transpose with a star, just like the adjoint. The problem with mathematics, of course, is that there's so many different notations, and some of them overlap, and some of them conflict. So the notation that you use is often very local, right? So in this class, we're using star to mean adjoint, and we're not giving any notation for conjugate transpose. Anyway, the question I want to ask is, what is the matrix of T star? And the answer to that question is, it depends on the basis, right? So the answer is, it depends on the basis. Of V and W. That was a trick question, right? And the result that we're going to prove is that if you take fixed orthonormal bases of V and W, then the matrices of T and T star will be conjugate transposed to one another. Okay, that's the answer. So I'll write it, I mean, we'll write this as a theorem in a second, but if you fix orthonormal bases of V and W, then the matrix of T and the matrix of T star with respect to these fixed orthonormal bases will be conjugate transpose to one another. However, if you take a non-orthonormal choice of basis, so just any old basis of V and any old basis of W, it's not true that the matrices will be conjugate transposed to one another. This depends on taking an orthonormal basis. Okay, and this is an example of why you sometimes want to take an abstract approach to understanding something. So for example, maybe in some class at some school, you could try to define the adjoint of a linear map by saying, oh, you take every linear map between finite dimensional vector spaces is given by some matrix. The adjoint is the conjugate transpose of that matrix. But that's not a good definition because it depends on a choice of basis. Whereas the definition of the adjoint did not depend in any way on any choice of basis for V and W. Okay, so this definition, this abstract definition of the adjoint, is a better definition because it's basis free. You could say, okay, well, let T be a linear map between V and W, fix orthonormal bases of V and W, and write the matrix for T. Then the adjoint of T star is the matrix defined, is the linear map defined by taking the conjugate transpose of that matrix. But that's like that's not nearly as clean a definition because it depends on a choice of basis. But anyway, that's just a rant from a young mathematician, maybe not that young anymore. Here's the results, which is the answer to the question. Whoops. So let T be a linear map from V to W. And suppose that E1 up through En is an orthonormal basis of V. And F1 through Fm is an orthonormal basis of W. Then the matrix of T star, this is a map from W to V, so with respect to this basis of W and this basis of V, is the conjugate transpose of the matrix of T with respect to this basis of V and this basis of W. Parenthesis. Okay, but for ease of notation, we'll just call this matrix MT star. We'll just call this matrix MT. Okay, and this is just, I like saying this is just a computation. Okay, so here's the proof. Okay, and just the idea is to get the kth column of the matrix of T, what do? You look at T of EK and you write it as a linear combination of the FJs. Right? TEK as a linear combination of the FJs. Of course, the FJs are an orthonormal basis of W, which means that it's easy to find the linear combination. So since the FJs are an orthonormal basis, T of EK is just the inner product of TEK with F1 times F1 plus dot 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 plus the inner product of EK with FM times FM. Okay, so this means that, so these entries will be the entries in the kth column. So the j kth entry, the thing in the jth row in the kth column of this matrix is going to be the inner product of TEK with FJ. Okay, now by the exact same reasoning, I can see, or we can see, that also the j kth entry of MT star is going to be given by T star of FK written in terms of the EJs, but the EJs are an orthonormal basis, so you can just take this particular inner product. But now we have an adjoint sitting there, so we should use, as always, the definition of the adjoint. Right, so let's just go back to the definition of the adjoint. The definition of the adjoint says that if you have, you could do this in many ways. If you have the T star part sitting in the right side, then you could switch the T to the left side. Or you could take the adjoint of the adjoint. It doesn't really matter, but let's just do it this way. Let's swap these. And then use the definition of the adjoint. Right? But now, this thing is exactly the complex conjugate of the kjth entry of M of T. The conjugate of the kj entry of M of T. So the kjth entry of MT is the complex conjugate of the jkth entry of MT star. That means that these two matrices are conjugate transposed to one another. And notice this really did rely on the fact that the E's and the F's formed orthonormal bases of V and W respectively. Okay, so I'm not in any particular rush to get to 7B. So we still have at least a day of lecture on 7A left. That'll be Monday. Probably, so your exam, I guess, your final exam will cover everything up through 7A. And then Wednesday, I guess I'll just try to cover at least a statement of the spectral theorem in the complex and the real cases, but we'll leave that to not be on your exam, on your final exam. And your homework, I'll give you problems on everything up through 7A, but since it's due on Monday, I'll have you not turn in the ones on 7A, but you can still do them for your own edification. Okay, so at this point in the class, all we have left is one homework due on Monday, covering up through 6B. And then your final exam, which covers up through 7A. We'll finish 7A on Monday. Wednesday, we'll cover as much of 7B as we can. All right.